In this part 7 of matrix and determinant series, we are going to discuss about transpose of matrix. Transpose of a matrix is obtained simply by interchanging the rows and columns of a given matrix. For example, if matrix A equal to this 3 by 4 matrix, then the transpose of matrix A, which is denoted as A super T, is determined simply by interchanging rows and columns. In other words, all the rows of matrix A becomes the columns of A transpose, and all the columns of matrix A becomes rows of A transpose. Matrix A has 3 rows and 4 columns. Since all the columns of A becomes rows of A transpose we have 4 rows. And since all the rows of matrix A becomes the columns of A transpose is going to have 3 rows. So the A transpose we are going to determine is a 4 by 3 matrix. Thus, A transpose equal to row 1 of A turns to column 1 of A transpose. That's column 1 of A transpose is 5, 2, -1, and 7. Row 2 of matrix A becomes column 2 of A transpose, meaning column 2 of A transpose is 3, 0, -2, and 8. And row 3 of matrix A is going to be column 3 of A transpose, that is 4, 1, -3, 6. As we already discovered, the order of A transpose is 4 by 3. If we analyze every row of A transpose, that is the same as the corresponding columns of matrix A. That's row 1 of A transpose is the same as column 1 of matrix A. Row 2 of A transpose is equal to column 2 of matrix A. Row 3 of A transpose is the same as column 3 of matrix A, and row 4 of A transpose is equal to column 4 of matrix A. In general, if the order of a given matrix is m by n, then the order of its transpose is n by m, meaning just switch these two numbers. Addition and multiplication of a square matrix with its transpose gives us a symmetric matrix. Let's check that by using an arbitrary 3 by 3 matrix. Let A equal to this 3 by 3 matrix and then calculate A plus A transpose and A times A transpose. Before diving into the addition and multiplication, let's determine A transpose, which is equal to column 1 of matrix A turns to row 1 of A transpose, that's 1, 0, 4. Column 2 of matrix A becomes row 2 of A transpose, that's -1, 3, -4. Column 3 of matrix A is going to be row 3 of A transpose, that's 2, -2, -3. Thus, A plus A transpose equal to matrix A plus its transpose. Since both matrices have the same order, that's 3 by 3, we can add them, and the addition goes in such a way that a given element of matrix A is added to the corresponding element of its transpose. That's row 1 column 1 of matrix A plus row 1 column 1 of A transpose, row 1 column 2 of A plus row 1 column 2 of its transpose, row 1 column 3 of matrix A plus row 1 column 3 of A transpose. By using similar pattern for the next rows, we will find 0 plus -1, 3 plus 3, -2 plus -4 in row 2, and 4 plus 2, -4 plus -2, -3 plus -3 in row 3. As we can observe here, on the main diagonal, we find similar elements added to each other. This is always true for square matrix because as we observe from matrix A and its transpose, their main diagonal elements are the same. In finalizing the addition, 1 plus 1 equal to 2, -1 plus 0 equal to -1, 2 plus 4 equal to 6, 0 plus -1 equal to -1, 3 plus 3 equal to 6, -2 plus -4 equal to -6, 4 plus 2 equal to 6, -4 plus -2 equal to -6, -3 plus -3 equal to -6. As we can witness from this final result, for every element below the main diagonal, its mirror image is located above the main diagonal. The main diagonal is a line drawn from these 2 at the left top to -6 at the right bottom. This -1 is the mirror image of this -1. For this 6 at the top right, we can find its mirror image at the bottom left, and the mirror image of this -6 is here. So the matrix we determined is a symmetric matrix. This is true for every square matrix added with its transpose. Next, let's solve A times A transpose. A is 3 by 3 matrix and A transpose is 3 by 3 matrix. Since the number of columns of matrix A, which is denoted by this second 3, is equal to the number of rows of A transpose, which is denoted by this first 3, we can multiply these two matrices. Thus, A times A transpose is equal to row 1 of matrix A times column 1 of A transpose. That product goes to here. That's row 1, column 1 of product matrix. In such multiplication, what we do is we multiply each element of a row by the corresponding element of a column, and then the products are added. For this case, first element of a row, that's 1, times first element of a column, that's also 1, plus second element of the row, that's -1, times second element of a column, that's also -1, plus third element of the row, that's 2, times third element of the column, that's also 2. For row 1, column 2, row 1 of matrix A times column 2 of A transpose is equal to 1 times 0 plus -1 times 3 plus 2 times -2. Row 1 of matrix A times column 3 of A transpose equal to 1 times 4 plus -1 times -4 plus 2 times -3. In moving to row 2 of matrix A, row 2 of matrix A times column 1 of A transpose equal to 0 times 1 plus 3 times -1 plus -2 times 2. Row 2 of matrix A times column 2 of A transpose equal to 0 times 0 plus 3 times 3 plus -2 times -2. Row 2 of matrix A times column 3 of A transpose equal to 0 times 4 plus 3 times -4 plus -2 times -3. For the ultimate row, row 3 of matrix A times column 1 of A transpose equal to 4 times 1 plus -4 times -1 plus -3 times 2. Row 3 of matrix A times column 2 of A transpose equal to 4 times 0 plus -4 times 3 plus -3 times -2. Row 3 of matrix A times column 3 of A transpose equal to 4 times 4 plus -4 times -4 plus -3 times -3. Just like addition, multiplication of a square matrix by its transpose yields similar elements multiplied each other on the main diagonal, and their products are added. This is true for multiplication of all matrix by its transpose. In casting forward, let's solve the multiplication and addition. 1 times 1 equal to 1, plus -1 times -1 equal to +1, plus 2 times 2 equal to 4. 1 times 0 equal to 0, plus -1 times 3 equal to -3, plus 2 times -2 equal to -4. 1 times 4 equal to 4, plus -1 times -4 equal to +4, plus 2 times -3 equal to -6. 0 times 1 equal to 0, plus 3 times -1 equal to -3, plus -2 times 2 equal to -4. 0 times 0 equal to 0, plus 3 times 3 equal to 9, plus -2 times -2 equal to +4. 0 times 4 equal to 0, plus 3 times -4 equal to -12, plus -2 times -3 equal to +6. 4 times 1 equal to 4, plus -4 times -1 equal to +4, plus -3 times 2 equal to -6. 4 times 0 equal to 0, plus -4 times 3 equal to -12, plus -3 times -2 equal to 6. 4 times 4 equal to 16, plus -4 times -4 equal to 16 again, plus -3 times -3 equal to +9. 1 plus 1 equal to 2. 2 plus 4 equal to 6. 0 plus -3 equal to -3. -3 plus -4 equal to -7. 4 plus 4 equal to 8. 8 plus -6 equal to 2. 0 plus -3 equal to -3. -3 plus -4 equal to -7. 0 plus 9 equal to 9. 9 plus 4 equal to 13. 0 plus -12 equal to -12. -12 plus 6 equal to -6. 4 plus 4 equal to 8. 8 plus -6 equal to 2. 0 plus -12 equal to -12. -12 plus 6 equal to -6. 16 plus 16 equal to 32. 32 plus 9 equal to 41. For this matrix, the main diagonal is aligned drawn from top left 6 to the bottom right 41. For every element above the main diagonal, we can find its mirror image below the main diagonal. So this matrix is a symmetric matrix. From the addition and multiplication of a given square matrix by its transpose, we figure out that the products we obtained are symmetric matrices. These facts are true for all square matrices. Knowing these facts help us to check the correctness of the final answer we obtained. If the matrix we obtained in such multiplication or addition is an asymmetric matrix, we have to trace back the steps and make correction in any of the steps we made wrong calculation. Since it's true that the final answer can't be an asymmetric matrix, let's start more properties of transpose of matrix. The first property, transpose of A transpose is equal to the original matrix, that's matrix A. Let's check this by taking this 2 by 2 matrix. A transpose equal to row 1 of matrix A becomes column 1 of A transpose, and row 2 of a matrix A equal to column 2 of A transpose. Transpose of A transpose denoted by A transpose the whole transpose equal to row 1 of A transpose becomes column 1 of A transpose the whole transpose, and row 2 of A transpose becomes column 2 of A transpose the whole transpose. Here we can clearly observe that transpose of A transpose is equal to the initial matrix, that's matrix A. Second property, A plus B the whole transpose equal to A transpose plus B transpose if A and B are of the same order. Again, let's check this property by using these two matrices, each with an order of 2 by 2. That's matrix A equal to 0, 1, 1, 2, and matrix B equal to 2, 3, 4, 2. Then A plus B equal to 0 plus 2, 1 plus 3, 1 plus 4, 2 plus 2, which is equal to 0 plus 2 equal to 2, 1 plus 3 equal to 4, 1 plus 4 equal to 5, and 2 plus 2 equal to 4. Then A plus B transpose equal to row 1 becomes column 1, that's 2, 4, and row 2 becomes column 2, that's 5, 4. Let's solve for this right hand side equation. For this calculation, let's determine B transpose and A transpose. A transpose equal to 0, 1, 1, 2. It's the same as matrix A because it's symmetric matrix. B transpose equal to row 1 of matrix B becomes column 1 of B transpose, and row 2 of matrix B becomes column 2 of B transpose. So A transpose B transpose equal to 0 plus 2, 1 plus 4, 1 plus 3, 2 plus 2, 0 plus 2 equal to 2, 1 plus 4 equal to 5, 1 plus 3 equal to 4, 2 plus 2 equal to 4. Again, these two matrices are equal. So A plus B, the whole transpose equal to A transpose B transpose is correct. Third property, R times A, the whole transpose equal to R times A transpose. Again, let's verify this by using a matrix A equal to this 2 by 2 matrix. A transpose equal to, the matrix is such that first row of matrix A equal to first column of A transpose, and second row of matrix A equal to second column of A transpose. Then R times A transpose equal to, these are outside the square bracket, multiplies every element inside the square bracket, that's R times W equal to RW, R times Y equal to RY, R times X equal to RX, and R times Z equal to RZ. To determine this left-hand expression, that's R times A, the whole transpose, let's solve R times A first. R times A equal to R times matrix A, that's R times W equal to RW, R times X RX, R times Y RY, R times Z equal to RZ. Then R times A, the whole transpose equal to, just by interchanging rows and columns of RA, we will find RW RY in first row and RX RZ in second row of RA, the whole transpose. Again, these two matrices are equal. So R times A, the whole transpose equal to R times A transpose is true. Property 4, A times B, the whole transpose equal to B transpose times A transpose, provided that AB is defined. Again, let's verify this by using A equal to AB, CD, and matrix B equal to WX and YZ. AB equal to row 1 of matrix A times column 1 of matrix B equal to AW plus B1. Row 1 of matrix A times column 2 of matrix B equal to AX plus BZ. Row 2 of matrix A times column 1 of matrix B equal to CW plus B1. Row 2 of matrix A times column 2 of matrix B equal to CX plus DZ. So AB, the whole transpose, is simply equal to this matrix. For solving B transpose times A transpose, Let's determine the transpose of each matrix. By interchanging the rows and the columns, we can find that B transpose equal to WY XZ and A transpose equal to ACBD. So B transpose times A transpose equal to row 1 of B transpose times column 1 of A transpose equal to AW plus BY. Row 1 of B transpose times column 2 of A transpose equal to CW plus DY. Row 2 of B transpose times column 1 of A transpose equal to AX plus BZ. Row 2 of B transpose times column 2 of A transpose equal to CX plus DZ. Again, since these two matrices are equal, A times B the whole transpose equal to B transpose A transpose is true. We used all 2 by 2 matrices for verification of the properties just for the sake of simplicity. But the properties hold true for any other matrices as well. By this, I wrap up this part. Please subscribe, like, and share the page. Goodbye for now.